Okay, we're going to continue on DRAM basics. Well, actually, we're going to finish up DRAM basics very quickly, and we're going to continue on some new DRAM architectures that we've been looking at to scale DRAM better. Can you hear me? Everything is okay? Okay. Okay, so this is the outline that I gave you yesterday. We've covered most of what you will learn in this mini lecture series. That's the outline of the course. We've covered most of the main memory basics. I'll go over them very quickly. And then today we're going to delve into the major trends affecting main memory. We've covered actually most of them, so I'm going to go over them very quickly again. And then go into solution direction one. How can we rethink the DRAM design within the context of the system level challenges that we're facing today. But just to jog your memory quickly, we were talking about DRAM controllers, and DRAM controller had a bunch of functions that made it very difficult to design. We needed to ensure correct operation. We need to service DRAM requests while obeying the timing constraints, and DRAM controller had many resource conflicts to keep track of. We wanted the DRAM controller to buffer and schedule requests to improve performance, and this actually is different from correctness, but this is very important, as we will see, within the context of especially multi-core systems where bandwidth is at a premium. And the DRAM controller also needs to manage power consumption. A little bit about that, we didn't cover this, but DRAM chips actually have power modes, which is not enough perhaps. This is something else that we need to rethink going into the future. They have relatively coarse-grained power modes. For example, you have active power mode where the chip is ready to access, and that's the highest power mode. You have all banks idle power mode where you can save some static energy, static power. You have a power down mode where everything is pre-charged in the banks. As a result, you can save even more static energy. And you have self-refresh, which is the power mode where you cannot access the DRAM chip at all. You can put the DRAM rank in self-refresh mode, and it basically refreshes itself, and that's it. This is the mode your cell phone puts your DRAM chips into when you're not using it for a long period. But this still does consume power. The self-refresh power is still extensive in your cell phone. If you look at some of the data that was presented by cell phone manufacturers, you see that most of the time your cell phone is actually idle, and it's actually refreshing your DRAM. That's one part of the system that's very difficult to power off. So we'd like to reduce this power consumption for other reasons as well, not for just scaling DRAM, but also to be more energy efficient in the entire system. But basically, you can use these power modes to power down a chip. Today, you cannot do it at the chip level, unfortunately. Power down a rank or change the power state of a rank. The trade-off is when you change the power state, it takes a while to get back to the power state where you can actually access the chip. For example, getting out of self-refresh actually takes on the order of microseconds. So it takes a long time to be responsive, to go back and service a request in DRAM. So people have looked at optimizing this. And going forward, I think rethinking some of these DRAM states, power states, is very interesting into the future because we want more finer-grained power management, perhaps, in addition to making DRAM more energy efficient. So this is a slide I already showed you, why DRAM control is difficult to design. Again, I'll breeze through it just to refresh your memory. We have lots of DRAM timing constraints. And if you look at a data sheet, there are more than 50. I think I counted 57 in Micron's 1 gigabit DDR data sheet that whose picture I showed you in the previous lecture. And you need to keep track of many resources. You need to handle DRAM refresh. You need to optimize for performance. You need to optimize for power also, which happens not to be on the slide. But some DRAM timing constraints. Again, this is a slide that I put up. But these are actually real constraints. So this doesn't have to exist, right? There are these timing constraints. People have put these timing constraints to maximize performance. You could say, you could have only one timing constraint to DRAM saying that an access takes this long. But right now we have timing constraints that says write to read delays. You could actually have a worst case timing constraint in DRAM that makes it very long. But people don't do that because otherwise you cannot optimize for performance. That latency, that worst case latency would be very long. It has to take into account all possible stabilization that needs to happen after a write happens and after you can open a row. So usually DRAM is evaluated with this timing constraint that's called TRC, activate to activate. It's called row cycling time. When can you issue the next activate after issuing the previous activate, the earliest time? And that has been the DRAM latency. This is a row conflict latency also called. And it's 39 DRAM cycles in this in this DDR3 1600 DRAM. And this is taken from one of our technical reports, which I encourage you to read. The technical report itself is about optimizing the DRAM write-backs. When do you go into the write mode in DRAM? And when you actually have row buffers open, how can you pull out cache lines that are dirty into that row buffer to maximize DRAM bandwidth? But basically, you have to obey these timing constraints. There's another timing constraint, just to give you an idea of what these are. There's 4 activate windows, for example. Anybody know what that is? Yes?
If you do more than this, you will sink more current.
That's it.
Can
Yes. So this is a power-related constraint. Basically, you cannot have more than four concurrent activates within this interval, within this window, which is 24 DRAM cycles. And the reason is if you have more than 4 activates that are happening within those 24-cycle window, the DRAM manufacturers do not guarantee correctness in terms of power, because your chip can melt, basically. That's an extreme, but that's how it is at the abstract level, right? So this is another constraint I think going forward we need to rethink. The DRAM has been designed to optimize for that constraint, but this is not a given rule, right? Maybe we make DRAM a little bit less more parallel, such that you can do more activates at the same time, but consume a little bit more power, and that in the end you can design a better system overall, right? Especially given the bandwidth that we need from DRAM going into the future. Okay, but DRAM controller today needs to obey that constraint. It cannot issue more than 4 activate windows within 24 cycles. And as you add these up, you see the complexity of the controller itself, right? How many of you have designed DRAM controllers? Or tried to? Oh, we have one brave person. It's actually fun to do that. It's very humbling. I don't know which one's the harder part, designing an x86 decoder or a DDR3 DRAM controller. Okay, so if you want to look at, if you want to see some of these other constraints, these are some of the papers that I will cover. I will not necessarily cover the background sections of these papers, but these background sections, the background sections of these papers that we've written discuss some of these timing constraints within the, for example, they discuss why there's an activate to read power constraint. Well, that's easy, I guess. Why there's a power constraint between activate and pre-charge, why there's a timing constraint between these different commands, and what they exactly are. So you can take a look at them. And this is one example, I guess, chart from one of those papers. Okay. I guess before going into these new DRAM architectures, there's one thing I want to cover. Because there's so much complexity in designing a system like this, when we first started looking at the memory controllers, we also thought about, can we actually do this in a better way? Can we actually have an automatic way of designing the memory controller? Why don't we design a memory controller that can determine its own policy instead of a human dictating this policy? Because obviously a human is limited in terms of their thinking. They cannot design a policy that can optimize for the long term. And as I mentioned earlier, you may want to send a request to a row buffer that's currently open that accesses that row, but that may not be the right thing to do, because that will stall another processor that's going to access that bank later on. And it's very difficult for a human to anticipate this. So why don't we design, and I think this is a general problem whenever you design a very complex system. It's very difficult for a human to get the best policy. So our idea was to have a policy that can adapt itself very well to different workloads, under different system conditions, under all of these different constraints. And the idea was to design a memory controller that adapts its scheduling policy decisions to workload behavior using machine learning. And we were, I guess, a little bit lucky in this case, because reinforcement learning, which is basically you do some action and you get some reward, that kind of learning maps nicely to memory control. I'll very briefly cover this idea. I won't go into detail. But going forward, designing systems with such machine learning techniques is a very interesting approach. Basically, our idea was to design a memory controller as a reinforcement learning agent that can dynamically and continuously learn and employ the best scheduling policy. At any point in time, the human may look at the policy and make no sense out of it, but the reinforcement learning agent has a nice policy. So what is the idea? What is the idea behind reinforcement learning? Reinforcement learning basically looks at things that make decisions as agents. So you have an agent here that interacts with the environment, And agent basically observes the state of the environment, maybe not all of the state, but part of the state, and takes an action based on that state, and gets a reward based on that action. And over time, it basically associates state and action pairs with long-term rewards. That's the idea. It keeps a table, basically. And whenever it sees a state later on that's similar to the state that is observed previously, it basically chooses an action that maximizes, that will likely maximize the long-term reward. That's the idea in reinforcement learning. This is very similar to Pavlov's dogs, right? If you learned about psychology, basically Pavlov did this experiment where he conditioned the dogs to react to the bell, right? By giving food when the bell actually rings. So that's very similar. You can view the entire world this way. Of course, this works only in cases where you can express the environment of an agent in the Markov decision process. And it turns out memory controller can be expressed as a Markov decision process. I won't go into detail in that, but you can see the paper. But you can see the memory controller, memory scheduler, as an agent that interacts with the environment, which is a system in this case. It looks at some state attributes, and I will show you some state attributes. This could be how many requests are pending in the request queue, for example. How many of them are hits in the row buffers? How many of them are writes? How many of them are reads? And it basically picks a command to schedule out of all the legal commands at that point in time. And basically, it gets an immediate reward. An immediate reward could be data bus utilization in this case. That's what we did. Basically, our goal was to maximize the long-term data bus utilization that you get. Basically, how often your data bus is utilized. This is the memory bandwidth that you're sustaining at any given point in time. Right? And you can actually basically update your table after you get this data bus utilization. And later, whenever you see a similar state, I'm saying similar, not exact state, because you may not be able to see the exact state later on. So you have to generalize from your past learning. And that reinforcement learning does that nicely also. There's a lot of theory behind it. You basically pick the command that has maximized the data bus utilization previously, before, based on that learning. So that was the idea. And reinforcement learning mapped nicely to the memory controller. And the hope is that this actually simplifies the memory controller too. Basically, how do you maximize a long-term reward? You don't look at the reward you get immediately, but you actually weight future rewards that you see based on the action as well. And there's a lot of theory behind it too. So I'm going very quickly over a lot of interesting machine learning theory. So a self-optimizing DRAM controller dynamically adapts the memory scheduling policy via interaction with the system at runtime. It basically associates system states and actions. Actions are commands. I'll show you those too. With long-term reward values, and schedules a command with the highest estimated long-term reward value in each state, and generalizes the state so that if state X is close to state X plus 3, then you basically generalize your learning. So for example, the dogs, you don't necessarily always hear the same bell, right? Maybe you hear a similar bell. You again think that there's food coming. So you'd like to do that in systems also, because there may be many, many states. And the controller continuously updates the state action values based on feedback from the system. So basically, you have a table that you keep updating. And this is the paper that talks about it if you'd like to look at it. But basically, this is what the control looks like. You have some state attributes coming from the transaction queue. The controller schedules an action and gets a reward. And over time, it updates its values such that it picks the best action given a state. So what are these reward functions? What are these state attributes? And what are these actions? That's the key in designing a machine learning agent at any given point in time. So our reward function, this will be limited. Our goal was to maximize data bus utilization. And we will see that this is not necessarily the best thing to do in a multi-core system, because if you want to maximize data bus utilization, perhaps there is an application that actually makes much better use of that data bus utilization such that it hogs that data bus bandwidth. So this is not necessarily a fair thing to do, but our goal is that. So basically, you can actually say you get a reward, full reward, if you actually have a read or write command scheduled, because that immediately utilizes the data bus. Otherwise, you get no reward. Sometimes getting no reward at this point in time is better than getting full reward at this point in time, because in the longer run, you get much more reward. Right? That's the idea of reinforcement learning. State attributes. Actually, we've looked at hundreds of state attributes in the entire system and picked these based on feature selection. You can run feature selection mechanisms. So number of reads, writes, load misses in the transaction queue, number of pending writes, and reorder buffer heads waiting for the reference row. These are presumably more critical requests because they're at the head of the reorder buffer in their processors. And request relative reorder buffer order. Where is this request in the reorder buffer of its core? So you can only do these if your memory controller is on the chip, right? Because there's a lot of communication bandwidth that you can have with the memory controller and the cores. In actions, these were the actions we looked at. We took refresh very rigidly. Basically, refresh had to happen. The memory controller always picked refresh over any of these commands if that refresh had to happen. That's actually not always true also, and if we have time, we can talk about that too. But these are the actions. So one interesting action over here is no-op. The memory controller can choose to issue a no-op, even though there's a legal command that would utilize the data bus. And we saw that the reinforcement learning agent issued no-ops, because in the longer term, you would get a better data bus utilization. So what is the impact of all of this? You can read the paper for details, but I'm showing you data from parallel applications here in 4 core systems. And these are different schedulers. These are 4 different schedulers. This is the geometric mean across these different parallel applications. Y-axis is the speed up over an existing controller, row hit first memory scheduler. It prioritizes row hits over others, and everything else being equal, it prioritizes older requests over others. And that's this one over here, 1.00. If you have no scheduling, first come, first serve, you get much worse performance. That's 0.58. That's not the baseline. So this means that actually utilizing the row buffer is a good idea, at least in these applications that have good locality. These are parallel scientific applications that happen to have good locality because data is partitioned that way such that you get good locality in DRAM. So if you have a reinforcement learning control, you can actually improve performance by about 19%, which is pretty good actually, in my experience at least. And this comes because you increase the data bus utilization significantly. And this 1.7 value over here is if you get rid of all of the timing constraints in DRAM except for the data bus constraint. So the data bus constraint you cannot get rid of, that's the bottleneck. But every other time constraint you can magically get rid of. So this is the ideal. I would say it's an unachievable ideal because you cannot get rid of some of the timing constraints. But yes, Arvind. Yes. So that depends on when your scheduling decisions are made. So what we did was we basically decided early on. So you made the exactly, it's overlapped. It's overlapped. So we have a design in the paper that actually looks at how you implement this. And we've actually implemented that. We didn't implement it in RTL in the end, but we would like to do that at some point. Sure. Yeah. So what we did was our design was for it depends on your processor cycle. Our processor was, I believe, 4 gigahertz, and our DRAM was probably 800 megahertz. So you had actually enough cycles, and you could implement this in less than 5 cycles. And with some pre-computation, if your DRAM gets faster, which is not necessarily a good trend in my opinion, because you lose a lot of power efficiency if your DRAM bus frequency increases, then you can pre-compute a lot of these values early on. Okay, so basically you can read the paper for other results. There are other results. There are a lot of other interesting results in the paper and implementation as well. So as with everything in, I guess, engineering, there are advantages and disadvantages to this approach. I'll briefly cover what I think are the advantages. Normally I would ask you, but we don't have a whole lot of time in these lectures. But basically the advantage of such a policy, I believe, is it adapts the scheduling policy dynamically. So at any given point in time, we don't actually know what the policy is because it's the reinforcement learning agent that's implementing some policy based on the state action, based on the mapping of the states to actions and the reward values. And also, it can adapt the scheduling policy to maximize a long-term target. If you think about the row hit first scheduling policy, it's a very short-term target. Do I maximize the row buffer hit rate at this point in time? It reduces the designer's burden in finding a good scheduling policy, in my opinion. The designer now specifies what system variables might be useful. These are the state attributes that you actually choose via feature selection. And they also specify what target to optimize, the data bus utilization, but not how to optimize it. So the designer doesn't need to come up with a policy. This is nice, right? You magically design a system. And I think going forward in multi-core systems, as complexity increases, looking at such techniques is great. What would your challenge be to such a policy? What would you think the biggest disadvantage is?
One of them might be the fairness.
That's right. Yeah.
How to implement hardware, like their software.
Okay. So you can take a look at the paper for the implementation. I believe this is implementable. In fact, people have implemented reinforcement learning agents in hardware starting from the 1970s for different purposes. And we use similar implementations. We don't have a whole lot of novelty in there. So you can actually implement this in hardware. You said something? The cost of changing context, what do you mean? When the applications change? Okay. So this is actually robust to applications change because you can relearn the policy relatively quickly because you have so much data going into the memory controller. And this is a paradise for machine learning, actually. You get a lot of data coming into the memory controller. So one thing I would say, it's a black box. And usually designers are human, and they don't necessarily like black boxes, right? They want to design something, and they want to understand how it works. And I think this is something that may need to be overcome going forward. Designer is much less likely to implement what she cannot easily reason about. And it's very difficult to reason about what this black box is doing at any given point in time. Even if you stop the memory controller at any given point in time and look at the decision tree it has, look at the state action pairs and the reward values associated with it, it's very hard to reason about what that decision tree looks like, actually. And given that you're stopping that at that point in time, what about over time? That decision tree changes, that state action pairs and what reward values that they map to changes, and it's very, very difficult to reason about this. But I think going forward, maybe this is something that can be overcome with education. I'm not sure. The second thing is what you had mentioned, I think. How do you actually specify different reward functions that can achieve different objectives? I think this is a little bit easier because that may not require a big mentality change. But how do you actually, in this case, we optimize for data bus utilization. And once you optimize for data bus utilization, you can actually map the problem to a Markov decision process relatively easily because you get an immediate reward. But if your goal is actually fairness, how do you define even fairness to begin with, which we will cover later on? If your goal is quality of service, how do you even define that? And how do you even express that to the memory controller such that you get a nice reward function that's specified based on your decision? So that's very tough to do, in my opinion. And this is a very interesting research area because it's a tough problem, but I don't know how to do it. But there are many smart people here also. That's a good question. I do not believe so because this is based on the state attribute. So it expands with your state space, but we quantize the state space anyway. So there's a lot of quantization that happens in the state space such that you can generalize in the state space. And with multiple memory controllers, if you have multiple memory controllers, you can have independent agents. Then there's another question, of course. Do you add additional state attributes such that the controllers are aware of each other? And we will cover that in a later lecture. Not for this controller, but for something else. So I think the scalability issues that come about are similar to scalability issues that you would already have in a memory controller. I don't think reinforcement learning adds anything new. Okay. So this is what I wanted to give to you also before we go into DRAM architecture. Do you have a question?
The verification of such designs wouldn't become very difficult, as you say, because engineers like to know what they are doing.
So that depends on the verification that you're considering. So the verification of how the reinforcement learning agent operates, that can be easily verified because you know exactly what it's supposed to do. But the algorithmic verification, what is the algorithm doing, and is it doing the right algorithm? You don't know because you don't even know the algorithm. Right? So that higher level of verification is not there, but the lower level of verification is easy. The verification of the hardware itself is easy.